Okay, so you're offering this lab for the very first time. You're the first ones using the robots. They're open to suggestions and feedback on how to improve them moving forward. So Euler angles, again, another way to describe the orientation of a frame with respect to another. The objective of today's lecture is then to understand the concept of Euler angles, calculate the transformations, the rotation matrices using Euler angles instead of using the composition, the projection of vectors that we used in the last lecture, and then apply the Euler angles to a given problem. So here, in the context of surgical robotics, here's one thing we can ask. We had this example in the last lecture, but let's go over that one more time. So we want to operate on a bone, and we want the tool to be positioned on the bone. So that is not sufficient, right? The only thing we would need to know to do that is the position of the bone with respect to a reference frame and the position of the tool with respect to the reference frame. That would allow us to position the tool on the bone. But that doesn't give us the orientation of how exactly is the tool oriented with respect to the bone. If we put a reference frame here where we want to operate and you want now the tool to align itself with that reference frame, that is to achieve that point with a given orientation, how should we orient the robot arm? So that's what we're going to see in the next lecture. Today we will be able to calculate these orientation given the configuration of the robot. We need to determine the end effector orientation, and then in the subsequent lectures we'll do the opposite problem. Given a desired orientation, where should we put each of the joints of the surgical robot? Another question that we can try to answer with what we're going to see today is how many joints or how many degrees of freedom do we need to orient the tool in a given position. One thing that those of you who had the lab yesterday noticed is that for a given position in space, there are many ways to get to that position. And there are certain ways the robot can orient itself. There's more than one solution. But we start to constrain those solutions so long as we are now, in addition of specifying the position, we are specifying also the orientation required to reach that position. We have, in the robot in the lab, we have 6 degrees of freedom. And when you're specifying position and orientation, how many variables are we specifying? Also 6. Also 6. 3 Cartesian positions and 3 orientations. The orientations that we're going to see today. As you can notice here from this picture, this robot arm has more than 6 degrees of freedom. What is the advantage of that? Is to achieve the same position exactly from different orientations and different entry points in the tissue, different configurations of the arm. Right, so that's one of the reasons it has more degrees of freedom than you would need to position and orient itself. So now when we talk about orientation of a tool, we need to talk about the orientation of a tool with respect to a reference frame. As we saw in the last lecture, we put a reference frame on a tool, and that a reference frame could be decomposed onto another reference frame, and the components of each of the vectors of the tool reference frame on the base reference frame would now give us the orientation. Today we're going to do the same thing, but we want to use instead just 3 different angles. Here they are. This is an analogy with an airplane. We put a reference frame in the center of the airplane there and have 3 axes. And you've probably saw this before. If you want to fully give the orientation of the airplane, you need to specify the rotation angle around each of those axes. One thing to notice here is that if you rotate the plane around this axis, you're changing the orientation of the other 2. So the rotation about 1 influences the rotation about everything else. So with these 3 angles, pitch, roll, and yaw, we should be able to describe fully the orientation of an object that is attached to a frame like that. So that's the idea of today's lecture. But before we move into that, let's go back to lecture 2 and just do a quick review of what we saw back then. Now, whenever we're talking about referencing something or writing the position of something, we need a reference point, we need a frame. And the frame here is given by a in three-dimensional space with the three unit vectors x, y, and z, and they are orthogonal. The combination of these three axes is the frame that we're going to call here frame A. So if that is the case, then we can now position any point in that frame by simply creating a vector that starts at the origin and goes to that point A, and then find the components of that vector on each of these. This is pz on each of these axes, and this is y, z, py. So the position of point A can now be given by this 3×1 vector. So by definition, remember from the last lecture, all vectors are column vectors unless they are transposed. But that is not sufficient to describe the position of a tool in a robot, for example, because with that you can only locate the tool tip with respect to, in a space with respect to a Cartesian reference point, but that doesn't give us the orientation. If we now take that frame and put a tool in that frame, we also want to know the orientation of that frame. And to do that, we came up with this rotation matrix, which is a 3×3 matrix, and which has three column vectors. And what do they represent? Each of these three column vectors from lecture 2.
It describes the basis vectors of B relative to A.
Exactly. The decomposition of each of the unit vectors of frame B on frame A. So the first element R11 is XB on XA. The second R12 is XB on YA, and R31 is XB on ZA. And you do that for all three axes of frame B. So each of these column vectors represent the decomposition of frame B relative to A. And you call this matrix the rotation matrix from B to A. So the projections of the unit vectors of B to A, and here is the formula for that. It's simply the cross product of these vectors. We also notice something interesting now. If you look at this as line vectors, what does that vector, for example, represent? It's the opposite, because now we have the components of A expressed in B. Right, so the columns of the rotation matrix are the unit vectors of B in A. The rows of the unit vector are the components of A in B. Yeah? That's from last class. If we transpose this matrix, what happens? We have, well, this row vector becomes now a column vector, essentially. Right? Which means now that by definition, the vectors that make up equation 4 are now the decomposition of A in B. So by transposing the matrix, we reversed the operation. The original matrix was going from B to A. If we transpose it, we go from A to B. Right? And that's what that means. So if you want to express one vector, one frame into another, simply transpose their respective rotation matrix. And another interesting observation that we should make here is the fact that the transpose is the same as the inverse when it comes to a rotation matrix. And that will come in handy later. The inverse of the rotation matrix is its transpose. Any questions here before we move on? No, it's all good from the last lecture. Yeah. Okay. But one thing to note, let me go back here from this rotation matrix, is that we have two reference frames and they have 9 elements. But it turns out that all these elements in the matrix are not independent from one another. First of all, we can note that all the vectors are unit vectors, which means that their magnitude is 1. So the magnitude of x, y, and z that make up rotation matrix R is simply 1. Now we already imposed 3 constraints on the rotation matrix. Another constraint that we can impose here, or we can see, is the fact that within a given frame, all the constituting vectors are orthogonal, which means that x dot y is the cross product between y and x is cosine of 90, which is 0. So all these vectors are mutually perpendicular, which means that their cross product is 0. So back to the matrix we had before, here we can already see that some of these calculations are not necessarily independent. We are just applying the same concept over and over. So if we started with a 9 element matrix, 3 by 3, and you can impose 6 constraints on the elements of that matrix, that mathematically means that we should be able to come up with that matrix by only specifying the remaining 3 elements, or with 3 elements. And those are the Euler angles. So let's define them. So a rotation matrix, as we saw before, is the rotation of one frame onto another. And with the Euler angles, we'll be able to specify that rotation with 3 consecutive rotations, one about each axis. That's the whole point of the Euler angle. We have 3 axes, we do a rotation about each of them, and then you can simply multiply the rotation matrix of these individual rotations to come up with the entire rotation matrix. So we take frame B. For example, with respect to A, we rotate frame B around x, y, and z by certain amounts. Those amounts are the Euler angles. And then we multiply the rotation matrix of each of these individual manipulations. So the first one, let's start here with the rotation about XA. So I have frame A and frame B. They were originally aligned, perfectly aligned. And I'm going to rotate frame B about XA by a amount gamma. Now that's the roll angle gamma. What should be the rotation matrix? Well, now you can go back to the definition that we had before and write rotation matrix as a function of gamma. So the first element of the rotation matrix is what again? Is x of the rotating frame B onto XA, which is according to the function of alpha here, or which is in this case 1. Yeah, because they are aligned, their dot product is 1. Right? It's cosine of 0. So this is indeed 1. The second element of the matrix is XB onto YA, which is 0. Why is that 0? Because they are indeed perpendicular. And then the last element there is XA onto ZB. It's also perpendicular, so they are also still 0. Okay, so that is 0. Let's put it 0 here. It doesn't want. Come on, there you go. Now let's move on to the second column. Now we are dealing with YA. And we are now looking at rotation that occurs, let me put it this way, around this plane here. Now we can forget about the x-axis. We simply have 2 planes that are on the screen here, and they are rotating with respect to an angle that comes out of it, an axis that comes out of it. So the first element is YB in XA. What is that? 0. They are again Perpendicular. The second one is YA onto YB. Cosine of gamma, right? So this projection down here, cosine of gamma, and we're gonna write simply C of gamma. The last one there is YB on ZA, which is sine of gamma. Now the last column, now we deal with ZB. So ZB on XA is on XA. Why Z is coming up, X is coming this way, so their projection is 0 because they are orthogonal. Then ZB onto YA, negative sine gamma. Yeah? Right, it's this projection over here, so that is indeed here. Sine, why is that negative? Because now the projection is on the negative y-axis, so that's negative sine of gamma. And then the last one is Z, the projections of both Z's, that is cosine gamma. Are we good? Questions here? No?
So, excuse me.
Yeah.
Minus sine gamma is ZB onto YB.
Minus sine gamma is ZB onto YA. Yeah. Alright, so it's this projection here. This is sine, it's negative because it's on the negative y. Alright, so if that's okay, let's do the next one. Now we have the same problem. We had frames A and B that were aligned. And now frame B is rotated around about YA by beta. That is, we're going to call the pitch angle. So the rotation is occurring on this plane here. Alright, so Z, this was originally coming out, it's basically going down. Y was pointing up, is turning like this. Alright, so we can take that plane where the rotation around the beta occurred and just take it out like that to visualize it better. So let's do the same now. XB onto XA, what is it? Cosine beta. XB on YA. XB on YA. Everybody see that that's 0? Yeah? Now XB on ZA. Negative sine of beta. Yeah? Negative sine of beta. Second column is now YB. What is YB? What is the entire column there for YB? What is this column here? Now we're dealing with YB onto XA, YA and ZA. What goes in there? 0, 1, 0. Exactly. 0, 1, 0. Does that make sense? And then the last one is ZB onto XA, which is sine of beta. ZB on YA. ZB on YA. 0, and then the last one, the projections of both sets is cosine beta.
Why is it not minus sine beta on the ZB onto XA?
Because XA is defined as the positive direction. X.
Is it negative because the ZB also the references to the negative axis?
No, ZA is coming that way. Not coming out of the plane.
Oh, yeah.
It's positive. Z was like that, and then it's coming down. So it is having a projection on the positive.
On the positive.
positive side of x. Yeah.
Okay. Yes.
All right, the last one is the yaw angle. We'll call that alpha, and that is going to be about z. Z A. So, first line there. What is the rotation occurring now? Well, the rotation is occurring, say, on the ground here. It's around this axis. So YB was like that, and YB is going that way. Right? You can take that plane out just to have a better idea of what is going on. So first column there is XB on XA, that is XB on XA, cosine of alpha. Second element, XB on YA, sine of alpha. Yeah? And XB on ZA is 0. YB on YA. YB on YA. Cos alpha. YB on, that's the second line there. That's this one here. Second one is YB on XA.
Is it one?
This one here is YB onto XA. Negative sine beta. Yeah? That's right. Negative sine, alpha, sorry. You're dealing with alpha now. Then the last element there is, what is that again? YB on Z, A, 0. And then the last column, what is the last column? 0, 0, 1. Yeah, 0, 0, 1. Because the y-axis, the z-axis are now the ones I want. Okay, so you have these three rotation matrices, and now what do we have to do? Well, we can simply combine them. If we do a rotation around x, y, and z, simply multiply them in a given order. But be careful, because if you do the rotation one way and you do the rotation the other way, you don't get to the same point. So the order of these rotations will matter. Here is an example. So we have this object, attached a frame to it, and you're going to rotate this object with respect to a fixed frame that is positioned like that. So first, let's rotate that frame around ZA. So we take the box there and rotate that around ZA. So what's the axis pointing up in the second rotation there, in the middle? That one. The one pointing up is still ZB. YA was coming out of the plane like XA was coming out of the plane. That was rotated 90 degrees that way. So this is XB. That is YB. Yeah. Now let's take that and rotate it one more time. Now around YA. And you're going to rotate it around YA by 90 degrees in that direction. That is clockwise. I guess counterclockwise. Counterclockwise. So what happens? XB remains XB. YB was going to the back there, now it comes up, and ZB was pointing up, now points to the front. So this is one set of rotations. Now let's go back to the starting point here and do the rotations in the opposite directions. We first did Z, then about Y. Now let's do Y and Z. So what are these axes here? Where is the one pointing down? Take this and rotate that around YA. Pointing down is XB.
Wait, it turns this way now. Like this.
It turns this way. Yeah. So YB doesn't change. And then we have pointing down XB and then pointing to the front ZB. Now we can do one more rotation. This rotation now with respect to ZA, again, the same fixed reference frame that we started from. Now pointing up, so we're going to rotate it that way. So YB was like that, goes to the back. XB doesn't change because they're rotating around it. And ZB was going to the front, now goes to the side. Now compare, so this is the second set of rotations. So those are two independent. We started from the same point, we applied rotations around Z and Y, and we went back to the beginning, did YZ. You can see that at the end result there is not the same. Right? So the order of these rotations matters. Now let's try a different type of rotation. What we did before is that we had a fixed reference frame that I have on the top here, and all rotations occurred with respect to a static fixed frame. But we could, instead of rotating with respect to these fixed frame, rotate the frame around its current axis. Instead of rotating now around A, we'll rotate around B. So the first one is the same. I didn't really change. We go rotating around Z, ZA and ZB have the same orientation. So that will give us pretty much the same as we had before. So here we have ZB, we have now XB and YB. Now the second rotation occurred before with respect to Z to YA. YA was fixed, but now YA is pointing, YB is pointing to the back. Now the rotation will occur around that one. So we're basically flipping it like that. You follow the rotations here? Yeah? So this is the first set of rotation. Did we get to the same point as before? No. When we rotate with respect to a fixed reference frame and with respect to its current axis of the rotating frame, we did not get to the same point, even though we follow the same order of rotations. Let's do the same exercise again in the opposite sequence. First Y, now Z, but again with respect to the moving axis, not the fixed one. So what is happening here? We are moving around YB like that. So YB stays where it is. X was pointing to the front, points down, and Z was pointing up, now points to the front. And now we do a second rotation. Rotation now that occurs around the Z, but now around the moving Z frame. And then you get to the other orientation there. So, same observation again. We started from the same point. We did rotations around about the same axis, but we did not get to the same point. In none of them, we actually reached the same orientation. Right? Even these ones here, when we rotated about a fixed frame, we did not get to the same point. Now let's do a magic trick here and take one set of those rotations as in the first example, and you're going to rotate the frame first about Z, then about Y, about a fixed reference frame. So that's the first set there. Rotations about ZA, then YA with respect to a fixed reference frame. And then let's do the same exercise, but now let's take the moving reference frame, the current reference frame, and revert the order of rotations. We're going to do YB and then ZB. And surprise, surprise, what happens? We end up in the same point. So this is to say that rotations taken about a fixed axis yield the same orientation as the same rotations taken in opposite order about the axis of the moving frame. So all that to reach this conclusion here. If you rotate one way with respect to fixed reference frame, if you reverse the order but do the rotations with respect to the moving reference frame, then you reach the same orientation. Is that intuitive? Not at all, at least for me. But, well, it works. Okay. So what do we have to do here? And now if you define these sequences of rotations, first of all, the sequence of rotation matters. The frame of reference that is moving also matters. And all we have to do now is to multiply the matrices we derived earlier in the correct order to now calculate the final orientation of the object. Here is the other example. So Z, Y, Y, Z. And the other one was Z, Y, Y, Z. Just in the with respect to different reference frames. So we reach the same orientation every time. Okay? Questions? No? All good? Alright, so now let's define this fancy rotation matrix. Let me erase this just to keep the suspense. Now, the sequence of rotation matters. The axis of rotation also matters. So whenever you talk about rotations with Euler angles, we need to specify those two things. We need to specify in which order these rotations are being taken and with respect to fixed or current frames. So the most common one is to do rotations about x, then y, then z, about current frames. About a fixed frame. So to describe B in A, you start when A and B coincide and then do a rotation about XA by alpha, then a rotation about YA by beta, then a rotation about ZA by alpha. First one was gamma, sorry. And these sequences of rotations now, we can calculate the final rotation matrix by simply multiplying them in the correct order. So whenever you're talking about a fixed axis, if you want to find the final rotation matrix, we will start with the first rotation and pre-multiply the subsequent rotation. So we start with our x, which is our first rotation, by the amount of gamma. Then comes the rotation around y by beta, and then comes the rotation around z by alpha. And the multiplication of these three rotation matrices now gives us the full description of frame B with respect to frame A, when after these three rotations are applied in that specific order. How do you multiply this? I'll multiply these two, then the next one. The final result here is a 3 by 3 matrix, which is the rotation matrix we are looking for in the beginning. Yeah.
Why are they to the left? Why are the multiplications to the left?
That's simply how it works mathematically. Yeah. Any questions here? No? Okay, when you multiply that, I'm going to spare you that work. When you multiply these three matrices, that's our new rotation matrix. A lot nicer than the dot products, isn't it? But they are the same. They are exactly the same matrices. But this one is with respect to these three rotations. So you have this 3 by 3 matrix here, fully describes now frame B with respect to frame A. We can simply input the values of alpha, gamma, and beta, find it, but we may also be interested, we'll see that that's useful later, in the opposite procedure. If we are given the rotation matrix, what are alpha, gamma, and beta? Well, we can simply take any of these expressions and try to solve for them. Trying to solve for a system of 2 or 3 variables and then find values for alpha, gamma, and beta. We don't need to do that. What will be the simplest one? How would we find the beta from this, for example? Let's assume that we did a bunch of rotations. We ended up with a rotation matrix that has 9 numerical values. From that, we want the value of beta. How do we get it?
Tangent inverse
Of
of the Pythagorean hypotenuse.
well, but we have the rotation matrix. So we don't know exactly where these angles are. Let's look at this one here. What is this one? Sine of beta. So if we end up with a rotation matrix where this value R31 here is known, what's beta? It's the negative arc sine of R31. Yeah? And you can do the same with any of these, so long as you can solve them. So given the rotation matrix, we can find the angles that way. I'm not going to use that one because it's too simple and we don't want to make things simple. No, that's not the reason. The reason is different, but here is the way, a more robust way to use that. And you see that we're using the function inverse tangent 2. You know what the function tangent 2 does? Does that ring a bell? It's like the inverse tangent, but it takes into account the quadrant in which the angles or the axes are. If you do, what's the inverse? For example, if you do the tangent of 90 degrees or negative 90 degrees, what is the result? Tangent of 90 or negative 90. Does anybody have a calculator?
Being defined.
Let's do, they'll be defined. Let's do let's do 180. 180. What's the inverse tangent of 180 or the tangent of 180?
1.5.
And what's the tangent of negative 180?
Tangent inverse?
No, just tangent.
Oh, just tangent. Minus 1.33.
No. Should be the same. That is just to say that the tangent function and the inverse tangent function may yield the same value for different inputs. So we can't really keep track of where the angle is. Is the angle between 0 and 90 degrees? Or is the angle in a different quadrant that would yield the same tangent result? Alright, so that's what this function, the inverse tangent 2, does. It simply accounts for that shift in the angle, if it is in the first quadrant, if it is shifted by 90 degrees or negative 90 degrees. So that's the reason you're going to use these functions instead of simply the sign there to account for the quadrant. So these equations here have been done for you. I'm just going to go through one of them, and then the other ones, if you're bored and have nothing better to do, you can derive them yourselves. But here is one. We saw that for sine of beta, for beta here, we have a tan 2 of negative this value times the square root of some, this divided by that, basically. Where did we get that from? Well, this came empirically from the observation that if you take R12, which is this one, so R12 is that one, and then I think there's a mistake here. Let's say you take these two here, these two elements, and you square them and take the square root. It's simply an empirical observation. What happens? If you square that and take the square root, we have cosine alpha, sine alpha squared. When you add them up, we have sine squared plus cosine squared of the same angle is 1. And then we are left with cosine beta squared plus, you can factor out cosine beta squared square root. So this whole thing here simplifies to cosine of beta. Right, because this basically is 1. Sorry, so it simplifies to sine of beta. That is 1, and then the last element left there is sine of alpha. Should be alpha. Beta is a type here. Sine of beta is squared. Wait a second. There's a typo here somewhere. So cosine is squared. That is a square. So we end up with okay. So that's the type is there's no typo. It's just I highlighted the wrong one. I factor out this, right, from the previous equation. So the result is that a cosine alpha squared plus sine of alpha squared is 1. And then you are left with cosine beta squared, square root, that is simply cosine of beta. So that the addition of these two is cosine of beta. If you look at this term here, R3, 1 is negative sine of beta. So if we divide them, what do we get? Negative sine of beta divided by cosine of beta, that's the tangent. Right, so that's where that expression came from. So basically, the whole thing here is the tangent of beta, and then beta is simply the inverse tangent of that. And again, why are we using this fancy, complicated math instead of just looking for inverse sine? Because we want to keep track of the quadrants in which these angles are. Okay, so for the other two angles, this math has been done for you. It's over here. This is the more practical terms. It will work better that way. So you don't need to know that. We can simply use this equation. So these are the equations again. One limitation of this equation is that when beta is 90 degrees, then one of this will be indeterminate because we are dividing some stuff by 0. So we have a special case there that has also been calculated for you. When beta is 0, 90, then use these three equations. Instead, when beta is negative 90, use those equations instead. Simple trigonometry. You're not going to go over how that was calculated.
I'm just curious why here we always use the reverse of tangent. Because in the previous slide, we have the sine beta equals to the negative R31.
Yeah.
So in that case, we can get it, the beta, directly from the R.
Yes, so that's what I was saying. We don't use that equation because if you simply use inverse of sine, we are not keeping track of the quadrant of where the angle is taken from. For example, if we have, let's say, a vector like this, for this angle, theta, this is the sine of that angle, which is the same as this one. But now the angle is that plus 90 degrees. So this is theta plus. Right, so if we use the sine, we don't know are we here or are we here. But the tan 2 does that for us. If we input, for example, x and y, so it will be a tan 2 of x and y. If both x and y are positive, we know that we are here. So whatever inverse of the tangent we get, we are there. If y is negative, then we know that we need to add 90 degrees to the angle. Basically, that's what is doing. All right, now let's do the other way, because this first way here was with respect to a fixed reference frame. But if you now do z, y, x, do the rotations in that order, but now with respect to a fixed reference frame, a moving reference frame, what should be the result? The same, the exact same one. So the equation should be exactly the same. So to get to the same equation, we start with the first rotation that now is rotation around Z, and we post-multiply the subsequent rotation. So it's first Z, RZ, then RY by beta, then RX by gamma. Right, and then it yields the same rotation as before, the same equation. Right, so this gigantic equation here holds for both of these conventions. So these are the most commonly used ones. A third one that is also used in a lot in robotics in general is rotations about Z, Y, and then Z again. It's the same idea, but then you have to recalculate all these matrices. So these are the most common ones. Guess what? Macadamic, the one who makes your robots, they didn't like any of these three, so they came up with their own just to make our lives a little more complicated. And their definition of the Euler angles uses X, Y, Z about current frames. None of the ones in the literature. They came up with their other one. I don't know if it was by accident or whatever, but I don't see any reason for a new one. So if that is the case, then you're doing now X, Y, Z about current axis. Right, so we start with the first, post multiply. We have X, Rx, Ry, Yz, multiply them again. So if you go back to our multiplication here, we need to swap the first and the third. Right? Yeah? And then redo the whole calculation, and that's the matrix that you'll find in their programming manual. Right? Because their convention for Euler angle is X, Y, Z about current frames. So that's not all. It's another difference compared to the literature is that they decided to swap alpha and gamma. So when you talk about alpha here, we are talking about rotations around Z. Everybody talks about, when we talk about alpha is rotation about Z and gamma is rotation about X. In the Macadamic manual, those are swapped. But I'm not going to restrict the theory based on what the manufacturer decided to do. We'll stick with the more general, more conventional guidelines. But in the lecture notes, these represent the same. Right? So, same idea again. If we are given this matrix, if we apply the rotation to the robot arm in a certain if you move the robot arm in a certain way, and you can do that in the lab, and you can get the resulting rotation matrix of the last frame, and you get a bunch of numerical values. How do we go from that now to finding alpha, gamma, and beta? Well, same idea. We can solve for some of the elements here, and that's what Macadamic uses in their manual. See here you see they opted for the quick version. Solution, simply arc sine of war 1, 2, 3 with some conditions. Right? So that's more for the lab. This will be repeated in the lab manuals whenever you need them. Let me just open this up again. Okay. Alright, so just as a reminder here, a little analogy: roll, pitch, and yaw, the three Euler angles that we need to specify to fully describe the rotation of frame with respect to another. Okay, so why do we need all of this? Well, because now we are moving towards the kinematics, calculating the kinematics of the robot. And as you saw in the lab, the robot has several articulated joints. They can take several forms. Most of them will have two forms: revolute or prismatic joints. Revolute joints are simply joints that rotate with respect to one another. The Macadamic robot has 6 revolute joints. All of them rotate. The other type of joint, this is the one we saw in the beginning of the lecture with that Da Vinci robot, is the prismatic joint. It's simply a joint that expands or contracts, simply moves linearly with respect to the joint where it is attached to. Alright, so this is the most common one. We have two links. They're connected with a joint, and there is an actuator there providing motion of one joint with respect to another. This is a revolute joint. This one here, we have some like a ball socket and like a pivot that it goes in two directions, and it could also be considered a revolute joint, but it now has 2 degrees of freedom. How do you implement that is a bit complicated, so we won't find that in robotic manipulators, but I've seen that before. The last one there is simply a shaft, and we have another shaft on top of it that it translates. That would be a prismatic joint. Same one here, some sort of piston like that. What kind is this one here? Simply 2 shafts that rotate with respect to one another like that. So that is a prismatic or revolute. It's a revolute joint again. And the last one is again a revolute joint, 2 axes that rotate with respect to one another. So what are we doing here? Well, each of these joints has an angle. Each of these joints is changing the orientation of the subsequent joints with respect to itself. Each of these joints has one of the angles in our rotation matrices. So each of them can be associated with a rotation matrix. Let's take this one here, for example. How would remember that a big T transformation matrix? How would that one look like? If you put, let's say, a joint, a frame attached to the first joint like that, to the first element, and then a second one that aligns with the second one, and here we have a angle alpha. If you think about that, a big rotation matrix, we have the 3x3 rotation, then on the side we have a translation vector, and on the bottom row was 0s and 1s, remember? So the rotation matrix is now a function of theta. What's the vector that is next to it? Translation vector. 0, 0, 0, because they are coincident. Yeah? Now let's take this frame, this one, let's take this one here. We can attach a frame. There. You can attach a frame to the base here. What should we see in their respective rotation or homogeneous transformation? The rotation matrix, what's the rotation matrix between them? It's a diagonal matrix, isn't it? Because all the axes are still aligned. There is no rotation between them. So the rotation matrix is simply a diagonal matrix. Let's assume that the translation here occurs along this axis, and this is x, and this is y. What should we see in the vector that goes next to the rotation matrix in the homogeneous transformation? x0, 0, 0. Right. Now you can see now why this is useful, because that's how we're going to be able to determine the position and orientation of 2 consecutive joints. What if we have 3 joints? What if we combine these? How do we solve the problem? How do we know, let's say I took this one here and put on the tip of that one. How do we now know the position of this frame with respect to the original one here?
So you combine the rotation.
Combine the two transformations. Simply multiplying the two transformations. Those are 4 by 4 vectors. If you keep matrices, if you keep multiplying them, we keep getting 4 and 4 and 4, 4 by 4 matrices until the point where the end result is simply a giant equation, like a giant matrix like that with numerical values. What are these numerical values indicating? Well, they are indicating, in the case of the rotation matrix, how the very last frame is oriented with respect to the first one. The composition of the coordinates of the last frame onto the very first one. Or how the Euler angles are, which are the Euler angles that would give us the same sort of matrix transformation. Does that make sense? Right, so the theory is boring, but the application is not. Because that's exactly what we use them for. So here is the case, actually. I had myself here and explain that instead. We have a frame all the way at the back here of this joint, this revolute joint. We can position this frame with respect to that, then this one, and that back. So here we will have 2 rotations and 1 translation, and another rotation. So you have basically 4 matrices, 4 homogeneous transformations, and we'll combine them, multiply them in cascade, so that now the last frame is known with respect to the first. So, being able to find where the tip of the robot is, given this angle, this translation, and that rotation, is what we call the forward kinematics problem. And it's basically a multiplication of these homogeneous transformation matrices. Now, another question is, given a desired position of orientation of this frame, where should these other angles, what should the other angles be? It's a much more complicated problem, and that's the inverse kinematics problem. So in the next lecture, we're going to do forward kinematics, then you're going to use MATLAB to try to make sense of it in lecture 5. Then you're going to have another forward kinematics in 3D space, and then you're going to do the inverse kinematics. Here is where things get a bit tricky. Any questions? Any comments? Any concerns? No? Alright, so I'll give you a few seconds to wake up and then let's do an exercise. Let's do exercise 1. A frame B is located initially coincident with frame A. We rotate frame B about ZB by theta, then we rotate the resulting frame about XB by phi. Give the rotation matrix that will change the description of a vector expressed in B, but in A. What do you have to define here? Order of rotation and determine if it is with respect to a fixed or a moving reference frame. Yeah. So what are the order of rotations? First we do zeta, we do about ZB by theta, and then XB by phi. Is this with respect to fixed or a moving reference frame? With respect to the moving, with respect to the current reference frame. So the rotation matrix then from B back to A, we start with the first rotation and then post multiply subsequent rotations. So we have the rotation around Z by theta times the rotation around X by phi. No, because this is with respect to a moving reference frame. So we start with Z, and then we add the other ones. Alright, so the rotation matrix from B to A is rotation around Z by theta times the rotation around X by phi. So we are rotating this frame with respect to itself, so you don't need to worry about Y, about A. Right? So the first rotation occurs around Z. So the rotation actually occurs on the two-dimensional space here, on the, let's say, the floor. We have ZB going up, X going down, and that is by an amount of, how much is that again? Theta. So what is the rotation matrix? Well, it's the rotation around Z by theta. What's the transformation matrix here? It's the rotation matrix. So we are going to redo all the same story. XB on XA, XB on YA, and so on. I think we can probably just write that now. It's the same stuff as before, right? Unless you guys want to rederive it. It will be cosine theta minus sine theta 0 sine theta 0 cosine theta 0 0 1. So this is Z by theta. What is the next one? Next one is about Y. But Y, about X, but XB. Alright, so theoretically it's rotating that way. So to visualize a bit better, I kind of moved stuff around. So you're rotating now on the screen plane. Alright, so the rotational curves on this screen plane here by phi. So it's a rotation around XB. And I'm gonna write here 1 0 0 0 cosine phi sine phi 0 minus sine phi cosine phi. What is the result of this multiplication? You guys remember how to multiply a 3 by 3 matrix with a 3 by 3 matrix? Yeah, what's the first element here? Cos theta times 1 plus that times 0 plus that times 0, you're left with cosine theta. What's the next element? Well, same matrix, now go to the middle here. So the only ones that are non-zero are, so this times that, this times this, you're left with, and 0 times that, you're left with negative sine theta cosine phi. Yeah? And then sine phi sine theta 0 cosine theta cosine phi sine phi cosine phi sine, oops, that should be the end result. So you can come up with your own convention for Euler angles and you can name it the way you want, so long as you have a final transformation matrix. Okay? Yeah? All right. Any questions here? Let's do exercise 2 then. It's a bit more interesting. Coordinate frame B is located at the base of a robot manipulator. Frame C describes the position and orientation of a depth camera that was originally coincident with B, then translated by that amount in X, Y, and Z, and then rotated by ZC by minus 20 degrees and about YC by negative 110 degrees. The camera detects an object having coordinates CP of that. So what are we actually doing? Imagine, for example, that the robot arm is operating on a patient and we have a machine, a X-ray machine or an ultrasound machine or something that is oriented. We know its orientation with respect to the robot frame, the base of the robot. The robot is here, the ultrasound probe is here, so we have a translation in 3D plus the rotation of the imaging tool. Within the imaging tool, we detect a point. Within the imaging tool frame, we detect a point. That point expressed with respect to the imaging tool frame is 0.5, 0.2, 3.1. Right? What do you want to know? We want to know how this point is expressed with respect to the base frame. Why is that useful? Well, because the robot, the tip of the robot is expressed with respect to the base. So if you measure anything with a camera, with an X-ray machine or whatever, that is not expressed in the same frame, we don't know how to position the robot there. And one example is targeted biopsy. You can take an ultrasound, try to find a point, some abnormalities in the tissue, a lesion, and then you tell the robot to go and sample the point right there. In order to do that, the point must be expressed with respect to the same frame as the robot and the factor is. Right, so that's what we're doing here. We have a point with respect to the imaging tool. We want to know what that point is with respect to a base frame. What do we need to know? We need to know where the tool is with respect to the base. At the first one, we know that it was translated by negative 2 in Y, 7 in X, negative 2 in Y, and 5 in Z. And then rotated about ZC. ZC means its own axis by negative 20. Then YC by negative 110. What kind of Euler angle are we talking about? We're talking about a Z, Y rotations with respect to a moving reference frame, because the rotations happen with respect to the camera frame, not with respect to the robot frame. Yeah? And they have an equation for that. That's our big equation. So far, our favorite equation, that's the rotation matrix there. What do we need in there? Alpha, gamma, and beta. Why can you use this matrix? Because this matrix was constructed in X, Y, Z about fixed frames, or Z, Y, X with respect to current frames. They are the same, right? So the problem can use this. All we need to know is X, is these angles. So what do we have here?
Excuse me.
Yeah.
I think I got confused because you just mentioned that this is the
Moving frame.
moving frame
Yeah.
equation, but what we use is the fixed equation.
The fixed equation for X, Y, Z rotation is the same equation for the Z, Y, X moving frame rotation. So those are the exact same. That one is X, Y, Z with respect to current frame. We saw that if we reverse the order of the rotations, but now we do that with respect to a current frame, we get the same results. So that's why we can use them at the same point, with the same problem. So what we have here is the rotation about ZC by negative 20 degrees. What is this? That's our angle alpha, isn't it? And then we have a rotation over YC by negative 110. What's this angle? Beta. What's gamma? Rotation around X. 0. 0. So all you have to do is go back to that giant matrix, replace gamma, beta, and alpha with those values, and you can find a rotation matrix. I'm going to write this down here for you because it is simply a mathematical problem. Numerical problem, I should have said. If you have any questions about how we got these matrices, let me know. You can go over it. I have to check here if there's a, I will check this later if there's a negative sign there. It might have a negative sign. That's the rotation matrix from C, from the camera frame to B. But that's not what we want. That's just one part of the problem. What we want is to express a point that was measured in this frame with respect to frame B. What else we need to know? Well, we need to construct the homogeneous transformation from it, because the homogeneous transformation also accounts for the translation. What is the homogeneous transformation? It's called that T from C to B. The homogeneous transformation has this entire matrix in it. Let's call that, just put it here like this, right? But it's the 3 by 3 matrix, basically copy and paste here. I'm just not doing that because I'm lazy. Concatenated with the translation vector. What is the translation vector? It's how much the camera was moved with respect to the robot. It was, what is that again?
PB origin.
Exactly, PB origin. And what are the coordinates of that? Negative 7 in X, minus 2 in Y, and, no, sorry, 7 in X, minus 2 and 5. So 7 minus 2 and 5. So this indeed is that a PB origin frame from the last lecture. So now we have a 3 by 3 and we have a vector 3 by 1 on the side here.
Do we have to input the 3 zeros and 1?
Exactly. So now we have to input 3 zeros that will now make this part here 4 and then 1 under here. Right, so remember that this numerical value is okay. What's next? What is this matrix? This matrix is the homogeneous transformation from one frame to another. Now we can input our frame, our vector that gives the position of point C, P in frame C, and express that with respect to the robot reference frame. How do we do that? We know that the point P expressed in B now is the homogeneous transformation times what?
Times the original.
The point P in C. Yeah. Right? But you can't simply put point C P in C because this is now 4 by 4. Right? And point C is a 3 by 1 by 3. Right? So we need to also add that a number 1 under it. So when you have P C, we complete that with 1. What is missing? What's missing? We're missing 1 under here to balance out the equation. Yeah? So what's the final equation? is that. Times, what's P? What is that point P again? 0.5, 0.2, and 3.1. And then 1 at the bottom. This is the shift of the camera frame. This is the rotation of the camera frame. This is the point observed in the camera frame. And the last line there is just for completeness. Yeah. So the result, after you do all the calculation, is 4.17, negative 0.75, 4.409, and 1 at the bottom there because we have added it to concatenate. So if you want to extract P8, those are just the top 3 elements in the result.